set of topics that we want to cover, and it's sort of borderline review, or let's say part of the preliminaries is random vectors and random matrices. Okay, so you probably have seen random variables, but maybe have not been working or are not comfortable working with random vectors and random matrices. So we want to develop some sort of calculus or some skills to manipulate random vectors and random matrices. And in particular, what we want to talk about is the how to compute or what it means for the expectation of a random variable, or how to compute it, and what is this covariance matrix. Okay. So in this topic, the correlation is a bonus. We'll see whether we're going to get it into it or not. So let me ask you, how many people know about the covariance matrix? 1, 2, 3, 4. Okay. So when we get to it, I'll ask you guys. So if you know about covariance matrix, the covariance matrix, you probably know the rest of the material in this part. But we're going to start. So before talking about random vectors and random matrices, so maybe let me just mention. So just start from random. So what is a random variable? Let's say we call what it is. Scalar random variable. So what is a random variable? Anyone? Yes. So a random real number, that's good. So it has a distribution. So you're not going to be very formal about it. I don't know how formal it was introduced to you. So it's like a function from that sample space to the real numbers. But I guess you're going to assume that intuitively you know what a random variable is. I'll say random number. Okay. X, a random number. I'm not going to worry too much. Usually like a real number. So it has a distribution. So what is the distribution of random variables in general? Yes. It could be any. So, like, can you describe what a distribution gives you? Like,
yeah, it's like gives you the probability that anyone can start thinking like.
Okay, so it gives you the probability that a random variable takes an arbitrary. So it's a little bit more complicated in general, but let's say if the random variable is discrete, it's exactly like described by the probabilities of the values that it takes. So if I have a, like, let's say X. So in general, so let me just mention in general. So I really don't want to teach probability, but general, just the bare minimum. So in general, what it is if you want to be very precise, it's a set function. So what it means to be a set function. So maps basically sets to numbers. So the probability that X is in A. So this is a set or a subset of R. And this is the probability that X lies in A. Okay, so for example, so this like distribution is this abstract object that tells you that this is this map. You give it any subset of R, almost any subset of R, and it gives you the probability that random variable lies in that interval. Okay, so for example, if I give you like -1 and 2, if you know the distribution, you can map it to the probability that x is in -1 and 2. So you know this number. Okay, so this mapping from all possible subsets. So the probability, like if I have like a singleton set, what is the probability that x belongs to the singleton set? This is just the same as the probability that x is equal to 3 in this case. So I can determine these probabilities. So the distribution is some object like that. So if x is a discrete random variable, x is a discrete random variable, the distribution is specified by just determining what the probability of each discrete value is. So if I specify the probability that x is equal to x, or if you want the probability that x belongs to this singleton set for all possible values of x that x takes, then that's enough. Then I can determine the probability of any subset because I can see like how many of these values are in there, and then just add up the probability of those values. So for example, if I have, let's see. So example, so x, we'll say, for example, we write it something like that. So like get one, like with probability 1/3, 0 with probability, let's say 1/2, 1/4. This is 1/2. With probability 1/4. So this is like a simple way of writing this. So probably x is equal to 1 is 1/4. Probability that x is equal to 0 is 1/2. The probability that x is equal to -1 is 1/4. So they have to add up to 1. So this completely determines the distribution of x. So if I ask you what is the probability that x is in -1 and 2. Okay, that's a -1 and 1/2. So can you determine this probability? What is this probability? Sorry? 1/4. Any other guess? 3/4, 2/4. So this would be like the probability that x is equal to, like belongs to basically this set, -1 and 0, right? Because this I can only take these values, and these values are included. So, and this is going to be the probability of x equal 1 plus these are disjoint events. So these sets are sometimes called events. So this is 1/4. This is 1/2. So 3/4. Okay, but the distribution, I don't want to like dig into this too much, but distribution is really the abstract set function that determines all these probabilities. So it's like, it's just enough for you to know these values, but the distribution is really that set function from all like these are called events, from the set of all events to the probabilities of these events. Okay, so the distribution, you might say the distribution of this is that, but really it's that underlying set function. So you're going to be a little bit sloppy. This is enough information to specify the distribution of x. Okay, so sounds good. So now this is a random variable has an expectation. So what is the expectation of this random variable? Or like what is the expectation of a random variable?
The value times the probability.
Great. So the expectation of x is like the weighted average of the values that X takes, where the weights are the probabilities of taking those values. So what is it in this case? Can you like expand a little bit?
1 times 1/4, so times 1 minus
1 times 1/4 plus 0 times 1/2 plus -1 times 1/4, which turns out to be 0. Okay. Sounds good. So another example, X is 1 with probability 1/3, -1 with probability 2/3. So what is the expectation? Yeah.
minus 1/3.
So 1 times 1/3 plus -1 times 2/3 is 1 minus 1/3 minus 1/3. Okay. So why did I give you this example? Because I want to ask a question. Okay. This may or may not be useful, but it's an important question to ask. So what is the meaning of this -1/3? So they call this the expected value. We expect to see this, but this guy only takes value 1 and -1. So what kind of expectation is that? It's like unrealistic expectation. We're never gonna see -1/3. Why do they call it the expected value? I only expect to see either 1 or -1. So if you answer this question, you know a lot of statistics. Okay. Let's see if anyone can answer. Why? Yes.
It means you're gonna see -1, 33% more time.
More of the time. Good. So you're gonna see -1. Like, okay. Some percent of the time more than the other. So twice as likely. So more of the time is the key. So more of the time. Anyone can expand on this. So this is the keyword, sort of. Expand a little bit. Okay, great. So law of large numbers. So this is really something about the law of large numbers, or like the frequentist. Okay. Yes. Interpretation of probability and expectation. Okay. So what does it mean for us to see like 1 with probability 1/3? What does it mean for us to see -1 probability 2/3? The frequentist interpretation, which ties very nicely to the law of large numbers, tells you that these probabilities are really frequencies of observing these values to repeat the experiment many times. So really what happens is if I have x1, x2, so in the framework probability, if I have IID draws from the same distribution of x, I'm going to write this like that. If you just observe one example, there's nothing to be said, okay? Probability doesn't mean much. Expectation doesn't mean much. So if you just take it as a coin with like 2 values, if you flip this coin, you either see 1 or -1. Doesn't mean to say like probability doesn't make much sense. The expectation doesn't make much sense. But if you repeat the experiment many, many times, the frequentist interpretation, or let's say the law of large numbers, tells you that like 1/3 of roughly 1/3 of x1 up to xn will be 1, and roughly 2/3 will be -1. Okay, another way of saying is that if I do like 1 over n, I from 1 to n, this is the indicator notation that I'm going to use xi is equal to 1. So this is going to be 1 if xi is equal to 1, 0 otherwise. So this counts how many of them are equal to 1 divided by 1 over n. This is going to converge to, it's like the fraction of times I observe 1, this is going to converge to 1/3. This is like basically the probability that a generic one is equal to 1, which is 1/3. If I look at these, this is going to converge to this probability, just 2/3. So this is an example of law of large numbers. So these are IID draws from the same distribution, the empirical average of take this indicator. So whether this is equal to 1 or not, this is going to converge to probability this event, but this is going to converge to probability that event. Sounds good? So that's the meaning of those probabilities. So given this, how can I do the same thing for the expectation? So what is it that converges to the expectation? There's something that's converging to the expectation here by the law of large numbers. Yes.
The average of all these.
Yeah, so just the average of the values, not the indicators. So this is going to converge to the expectation. Okay, so there is something going on that's like, this is the expected value, and the empirical average is going to be expected to approach that. Okay. So that's the meaning of expectation, that's the meaning of the probability. These are frequentist interpretations. So if you understand this frequentist interpretation, you'd like understand like what confidence interval means, or like what p-values are. These things are tied to this. So there's no easy way of interpreting just a single observation. But if you repeat it many, many times, IID draws from the same thing, and the probabilities make sense. So you use like frequency dropping when n is large, and the expectation makes sense. It's like you see this empirical average crossing. Okay. And this can be like -1/3 because you're averaging like a lot of things, a lot of ones at -1, and it could converge to a non-integer. Okay, so crash course in probability. Good. Law of large numbers is important for statisticians and also for interpreting. So this is like the formalization. This is like classical. Frequentist interpretation means that probabilities are interpreted as frequencies of occurrence in many draws from the same experience. Okay. So it's a really weighted average of the values of x by the probabilities, but the meaning is this. Given like what makes it interesting is this law of large numbers. That if you repeat the experiment many times, take the empirical average will be close to the expectation. So averages are going to converge to the expectation. And so that's basically why statistics turns out to work. Okay. Sounds good. Questions? Okay. We'll come back to this, but now what if x is a continuous variable? Just a quick reminder that the distribution, so if I want to specify the distribution, oftentimes it's not possible to do it by specifying what value, the probability of the individual values that x takes. Why not? Let's say. Anyone knows? There are infinite amount of them, so we can't specify all of them. That's one point. But let's say if I want to specify a subset, is it useful? No, why not?
Well, like an x can't be in specific value. This
Can you say it louder?
an x can't be a single definite value.
Okay, so the x cannot take, in other words, the probability, yeah. So the probability that, for example, this is equal to a certain value, this is going to be 0. And this is going to be the same for all of them. So it's not useful to specify these specific values. So this goes back to like some like mathematical aspects of probability. So you can't specify the probability of individual, taking individual values. So what is it that people do instead? Sorry? Okay, so they write it as an integral of okay, some symbols here. So what is f of x? Yes. Okay, so this is called the PDF. So what they do is instead they oftentimes for this like classical continuous variable, they write this probability as an integral of something. Okay, so that something is called the density or probability density. Anytime you integrate something, it's the density of whatever you're integrating. So this tells you, for example, what these functions are like you can think of them as like these are really usually you give the meaning of the distributions, but they're really densities. You want to be precise. Sometimes you say the distribution. This is the distribution, but the distribution is really that set function. This is like the density of the distribution. So suppose I have something like that. You can think of it as like a. We used to have a teacher, like professor. He would say, think of these as piles of sands. Okay, so you have like a pile of sand. The height over like a particular area tells you like how likely. So if I want to determine what is the probability that X lies in this set, I'm just going to look at how much sand I have on over this. So the amount of sand over this is going to give me the probability, which is just the integral of this f over that. So this is a nice way of determining the probabilities, and it's consistent, so it works. So if my set is like this, so this is this interval union with this interval, I'm just gonna compute all the mass that lies over this part of the space, and that's just integrating over this. So you can determine the probabilities of any event. So it's called probability density function. So this is a nice way of dealing with continuous variables. Okay, so you specify how you can think of the probability as mass, how this probability mass is spread over the space, and the parts of the space that have more mass on them, they're more likely. So it's more likely to observe X around here than around here. And if I wanted to specify the side probability of X landing inside the set, I'm just gonna see how much mass I have. It is done by integrating over that set. Okay, and then is this sort of clear? If we remember, right? So the distribution in this case, so the distribution of X is specified completely by its PDF, or I'm going to call it density just. So you don't have to specify the set function. The density is just from X to reals. It's easier to work with. It's just a regular function. Whereas the distribution really is a set function. Okay, sorry. Good. So how do we compute the expectation here? Yeah. So somehow this is like the probability you want to. This is really the probability of X lying in a little interval around X. Okay, so if I think of this little small interval around X, f of X times dx is the probability because it's the density, so you have to multiply by the length to get the probability. And So this is just saying I'm averaging all the probabilities and adding up the probabilities. This is like summation. This one is just gonna be the weighted average. So this is the probability that x lies in x plus px, let's say. And over this little interval, the value of x is really x almost. And so x times the probability of x and then the average. So this is still a weighted average, but in the form of an. Okay. You're not going to have much use for these formulas, but it's good to know. Okay, so if I give you a general PDF, you should be able to calculate the expectation, and the meaning is still the same. So what is the meaning of this? If I repeat exactly this, so if we're like sample from IID from X, so this law of large number is general. If I form this is going to converge to this integral, basically, this weighted average. Okay. Good. So a very brief reminder of what a random variable is, what is the distribution, what is the density. In this case, this thing is called probability mass function. So when you specify the probabilities of individual values that this takes, this is sometimes called the PMF. This is called the PDF. Okay. Questions? So now random vectors and matrices. So a random vector is really nothing but a collection of these random variables. So if I have, I usually write it as y, let's say, but you could have x. So let's say y, a vector of y1 up to y to yn, where yi are random variables. Okay, so if I have a bunch of random variables, I stack them in a vector, that would be a random vector. This goes similarly for a matrix. A random matrix is just a matrix of random variables. Each coordinate is a random variable. Okay, so how do we define the expectation of y? Anyone? It's a very natural way of doing it. Yes.
It's just finding the expectation of all random variables.
Yes, you find expectation of all the random variables and just replace them with their expectations. So just stack these. The same dimension as the vector. If you have a random matrix, it's the same idea. Okay, so you have a matrix of random variables. The expectation of this random matrix is the matrix of the expectation. Then you put the expectation in front of everything. So what we care about really usually is how to compute. So the expectation of, let's say, A times Y, where A is a matrix. So these things are of interest to us. So this is, let's say, n by 1. This could be m by n. So this is a new random variable. So if I have an m by n, so let's say A is m by n, y is n by 1. So AY would be m by 1. So AY would be a new, so let's say this is deterministic. This is random. So this would be a new random variable. Right. Okay. How do you calculate the expectation of this? You just write down what each entry is. Okay. So if I want to calculate, for example, the ith entry, so this is a matrix, the ith entry of this would be basically the expectation of the ith entry of this guy. So if you imagine what I did here, so the ith entry the ith entry of this is just the expectation of the ith entry of the vector, right? So that's the idea. This is also like a vector. So the ith entry of the expectation would be the expectation of the ith entry. And so this is going to be expectation of this is easy. So I can expand. Anyone knows how to expand? What is the ith entry of A times Y? Form, yes. You're gonna get there, so it's fine, great, but like, forget about the expectations and expand it. So the ith entry of A times Y. We have a formula for it. We have A. This is Y. Right, and here M. So the ith entry of A times Y would be this ith row times Y. So the AI J, Yj summation J from 1 to N. Okay, that's how you would write it. So each entry gets multiplied by the corresponding one. Does that sound good? So if you go back to the definition of matrix multiplication, the ith entry of the result. So this is AY. So the ith entry here would be just basically the inner product of these two, which is just the summation. Aij times Yj is sum over J. So now there is a property of expectation that is very useful, which I haven't talked about, which is called linearity of expectation. So expectation is a linear operator, which means that it passes through linear combinations. So can anyone tell me what do I mean by that? So what is the implication of linearity of expectation? Yes.
One of them is expectation of X plus Y, and the other expectation of X plus expectation of Y.
Yeah, so expectation of X plus Y is expectation of X plus expectation of Y. Also like expectation of, let's say, alpha X, if alpha is constant, comes out. So from these, it follows that expectation of any linear combination like this is going to be summation Ci expectation of Xi, assuming the Ci's are not random. Okay, so I can pull out the sum and the coefficients and expectation apply directly to them. So this is the linear, it commutes with linear operations. So if I do that here, I would get summation J from 1 to N, expectation of an Aij comes out. You get expectation of Yj. Okay. But if you really think about this, this is really similar to this operation, but I'm applying this operation to the expectation. I'm really computing the ith element of A times the vector, which is expectation of Y. So this is really A times the expectation of Y. The ith element. Okay. So just think a little bit about this, but this is still the key. So I pull everything out and get that. Now this is the J entry of this. So if you call this like mu, call this mu. This is really mu J. So I'm really computing A times mu with the ith entry. Okay. So if you put it back together, you see that the ith entry of this is equal to the ith entry of this, and this holds for any I. So these two vectors are really equal. So what we really proved is conclude. So this should go somewhere else. Small. Little piece here. So what we really showed is proved. So this holds for all I. So we proved that the expectation of AY is A times expectation of Y. So this is another manifestation of, this is really manifestation of linearity of expectation. I can pull out this matrix. Because it's constant, it's a linear operator, if you remember. This is a linear operator, so linear operator. The expectation is a linear operator. This is a linear operator that it interchange. Or not the order, but like pass it through. So E goes actually like interchange. It's like commute. So this goes in to prove that. Okay. So you can move expectation past linear operators, which are matrices. Assuming that A is deterministic. Sounds good? So this linearity expectation is useful because you don't have to take the integral, or you don't have to do like these weighted averages. So this gives you, so we don't need to do, for example, any calculation like this. If I know the expectation of these individual random variables, I know the expectation of this new random vector. By a simple matrix multiplication. So this calculus that we develop is helpful to deal with linear operations. So what I did just summarizes, or this slide summarizes what I just did. Okay, so this is the result. Expectation of AY is equal to A times expectation of Y. Sounds good? Questions? Comments? No questions? Okay, so we can extend this a little bit. Suppose I have now A, let's say A is a random matrix. So the expectation of A, as I mentioned, so the ith element of the expectation of A would be the expectation of the ith element of A. It should be better, like maybe better to write it as Aij. So yeah, so let's do A, capital A. So that's the definition. I'm going to skip the example. Once you have the definition, you would be able to like extend that result that I mentioned to this result, which is very similarly proved. So if I have a random matrix, B and C are non-random, and let's say I can form BAC. So this is a valid matrix multiplication. So the inner dimensions here and here match. So let's say all of them are matrices, and this is the valid matrix multiplication. The only matrix here that's random is A. I can pull out B and C and apply E directly to A. So this is a simple extension of what we did, and it follows again from the linearity expectation. The way to prove it is, again, we get the ij entry of this. The expectation, so the ij entry of this would be, so proof is like expectation of the AC, the ij entry, by definition would be the expectation of the ij entry of this inner matrix. And then you write down what this is as a linear combination of the elements.
It's on the web for then. Check it out.
Not too intelligent. Okay. PAC, IJ, the Yeah, so you write down what this is, would be just a linear combination of elements of A basically is grades that are come from B and C, and then you can pull everything out except A's, and then they're involved in follows. So you're going to use this a lot, and once you use it a lot, you get comfortable, more comfortable. Okay. One thing to note is that I can't reorder the elements because matrix multiplication is not commutative. Okay, so if I can multiply BAC, it doesn't. So BAC, if this is a valid matrix multiplication, this is not necessarily equal to CBA. This may not even be defined in terms of the dimension. So they have to conform to for the matrix multiplication to be defined. So you can see the order is preserved for BAC. So you have to write it in the same order. You can't just rearrange. But otherwise, E goes inside. Okay. Yes.
What do you mean by BC are non-random?
What do I mean by that? Anyway, I just mean that they're not random.
You mean they are also vector, random vector?
They're matrices, but they're not random matrices. Right. So, for example, see if I have an example. Okay, so A could be, let's say A could be like, let's do a simple example. A is x1, x2, like 2 and x2. Okay, and then x1, okay, doesn't work. X1, x2, their IID normal 0, 1. Okay, these are random variables, so this is a random matrix. Okay, I'm going to take B to be 1, 3, let's say, and C to be -1, 0. Okay, that's what I mean by non-random numbers. Okay. So I can form BAC. So B is 1, 3. A is x1, x2, 2, x2. This is -1, 0. Right. So you multiply out. What do you get? You get something, but in this case, it's going to be a 1-by-1 matrix. It's just going to be something. It's a random variable, right? Anyone cares to multiply? So the way to multiply this times this times that, that's the first element. So you get -1 x1. And then this, okay. This times, so basically what you do is like you pick each one of the 4 pairs. So this one would get multiplied by the second row and the second column. So it gets multiplied by that. This one, this is going to be the first row and the second column. So it gets multiplied by that, and so on. So the way to do it is like that. So without doing it, you can do like first this and the other one, but it's easy to do it like -1. So you get 1, 1, -1 x1. So you get -x1. Okay, I can't. Then you would get 1 times this times that, which is 0. Then you get this times this would be times that, so you get -6. I'm not wrong, right? So the second row, the first column, and then you would get this times that, which is again 0. So you can multiply out, see if I did it correctly. Right? Okay. So what would be the expectation? This is like just a single this happens to be in general the matrix, but here it's just 1 by 1, right? So it's like 2 by 1, 2 by 2, 2 by 1. So you get 1 by 1. So it's really a random variable. So what is the expectation of this? Yes. Why?
Because X1 is ID with 1, 0, 1, and it's shifting it 6 to the left.
Yeah, so like you can do linear expectation. So minus expectation of x1 minus 6. Okay. The expectation of x1 by definition is 0, so you get negative 6. Okay. Sounds good. Linearity expectation. So what that result means, so let's use the lemma. So in this case, it was actually easier to do it that way, but in practice, not in practice, but in theory, so the theoretical developments. So what I mean here is like that result is saying something like that. Okay, so it would be like 1, 3, here would be the expectation of A, and here would be negative 1, 0. So it was easier to actually do this calculation if you want, just a trick, because the 0 is going to kill this. So if you remember the way that I told you that there is a different way of doing matrix multiplication, so you would, you can form the linear combination of the columns with those ways. So this is really -1 times the first column plus 0 times x1, x2, x2. So you can get rid of the second column. So this was easier. And then you just multiply this by that. So you don't have to do a lot of work here. Okay. Anyway, so that was like a little trick. So what is the expectation of A? Yes. Oh, maybe, okay. Someone else, maybe, okay, yeah. 0, so basically would be the expectation of x1, expectation of x1, x2, expectation of 2, expectation of x2. Okay, and this happens to be 0. This happens to be 2 because it's just constant. This is also 0 by definition. This one is, really? Why? Okay, good. So here's, you're using expectation, great. Sorry, the independence. So by independence, it would be expectation of this times the expectation of that. So expectation has this property that if you have two independent random variables, the expectation of the product is going to be the product of expectations. So this is going to be 0 times 0 would be 0. Okay. Sounds good. So what I end up getting is by that procedure 1, 3, 0, 0, 2, 0, negative 1, 0. And if you multiply, you just get this times everything is 0 except this times that times the first one. So you get 3 times 2 times negative 1, which is negative 6. And these two match. This matches that. So you could do it either way. Okay. Sounds good. Okay. Expectation. So this is like a more fancier example, but it's good enough for now. Any questions about this part? So we know now the expectation of a random vector and a nice result. How to deal with expectation of things like this, products of matrices or vector size matrices, where one of the matrices is random, the rest are non-random. Then you can handle the expectation by doing this manipulation, the simple linearity of expectation. So the key word here is linearity of expectation. So if you understand that, you could do it from scratch like this, or you could use this result. So we'll see this in action more. Okay, so now let's talk about covariance matrices. So now's the time to ask you guys. So some of you said that you know about covariance matrices. So any of you want to tell us what a covariance matrix is? So there are actually some steps here. So we know first you have to know about variance. So covariance matrix is an extension of the variance, or like a generalization of the variance. So what is the variance of a random variable? Variance. Yes. Great. Yeah. So that's a good answer. So, so expectation of x, you can think of it as a measure of where the center of the distribution is. Okay. So if you have like this pile of mass, the density, usually the expectation is like close to the center. Okay. It's not always like that. You could have like something like that. Right. The expectation might be here. Okay. Because you're rating things by average. But if it's like unimodal, this is bimodal. If it's unimodal, it's usually close to what you'd expect. You find most of the mass. So it's a notion of the center of the distribution. The variance is a measure of how spread out things are. So two distributions could have the same expectation, but this could be like very sharply concentrated near the expectation. So these two guys have the same expectation, but one of them is more concentrated. So which one has a smaller variance? This one has a smaller variance. This one has bigger variance. Variance tells you like the bigger it is, the more like spread out the distributions. So among these, like you could have like the same expectation. One could be very sharp. The other could be very flat. So this higher variance. This is lower variance. So intuitively, if you remember what the density is, for it to have a lower variance, it has to like peak higher, because the total mass is 1. So I have to squeeze like mass of 1 into smaller space, so the peak goes higher. And so the one that has lower variance is more likely to be found near its expectation compared to the one that has high variance. So variance tells you something about the concentration of the random variable and how likely is it that you find the random variable nearest its expectation. In the extreme case where this just goes like blows up, it's like this distribution that approaches the delta, like with high probability, you know that the random variable is always close to the expectation, maybe it's like exactly the expectation. So that's sort of the meaning of the variance. Sort of clear, right? What is the formal, like mathematical definition? I can define it in terms of the expectation actually. Yes.
Expectation of x minus mu times mu.
Okay, what is mu?
Mu is the expectation.
Okay, good. So you take the deviation, so x minus mu. Okay, so if this is mu, you look at the random variable that's x minus mu. So this is sometimes called the centered random variable. Centered. So sometimes I write x tilde. So x minus mu is, or x minus expectation of x. And in terms of this centered variable, it's just the second moment. Okay, x tilde squared. That's the second moment. And so that's the variance. So it's sort of a central second moment. the like second order. So these are called moments. So the expectation is the first moment. This is sort of central second moment. Centered because this is going to have expectation 0. So expectation of x tilde is going to be 0. Why? Because of the linearity expectation, this comes out. This is mu minus mu. So the centering makes the x tilde 0 mean. So we remove the mean. So now two distributions that have the same mean. So the mean is not going to affect our calculation anymore. So you're just going to see how spread out this is around the mean. If I just square it, I'm not going to get the central piece because this could be like 0 could be here. If I just square x, I'm just going to measure the magnitude of x on average. I want to measure the deviations from the mean. And so when you subtract from the mean, x tilde will be centered here. So if this is the distribution, x tilde would have this distribution shifted to 0. So the peak would be shifted to 0. And now I can measure the spread. Okay, so this is now like, this is going to peak, like, it has the same shape as the, so for x tilde, that is the density has the same shape as that of x, but shifted to 0. Now I can take the expectation squared, and it tells me how strongly concentrated near 0 I am. Why it tells you that is you have to think a little bit about that. But, because it's always non-negative, it can't be 0 or negative, so it just adds up everything positively. So, any deviation like squared is going to be positive times the mass. So measure really deviation. There's no cancellation of signs. Okay. So or think a little bit about that, but that's basically variance. Okay. And the centering is called centering or centered. And the variable is simplifying things somehow for us to simplify. So because of the centering, if you think about it, the variance is invariant to shift. So if I shift, so variance of, let's say, x plus 2 is equal to the variance of x. Because when I try to define it, I'm going to center this and center that. Once I center, I'm going to remove the shift. So the centered version of these two are going to be the same. So it's going to be invariant to shift. Variance is invariant to shift. Okay. Good. And there is another point here. I can expand this, and there's another way of writing this, which is this minus mu squared. This you can expand and verify. Okay, sometimes it's easier. The second moment minus the first moment squared. That is also useful. Good. This was a crash course on variance. So what is the covariance thing? Any questions about the variance? So you're statisticians, hopefully you know about the variance. I don't spend too much time on it. What is the covariance? Yes.
So like how related to different random variables are.
Yes, okay, good. So if you have, so it's basically a property of, let's say, two random variables. So I have x and y. So a pair of random variables. Now, a pair of random variables, you can think of it as a vector. So it's fruitful to think of it as a vector. And these vectors also have distributions. Okay, and we talked about the expectation of this. So the expectation of this random vector is really the property of this distribution. The distribution, let's say if these are continuous random variables, the distribution is also can be represented by density. But now the density would be a function from R2 to R. Okay, so if I want to plot the density of this, it's going to be really challenging because it's not going to be a univariate function. Okay, let's do maybe x1, x2. So it's random vector. How do they show the so it could be like x1, x2, and then this is like the density is f of x1, x2. Okay, so it tells me like how much mass are in like different areas of x, like x1 thing, like x1, x2 thing. So it could be like something like that. I have to like do this. So imagine like a function that has some sort of a like a surface. Not good. But it's like a surface. Not the surface at the same time. So the area under the surface. So the easiest way usually that people deal with this is instead of looking at this way, look at the level sets of the density, at least in R2 would be like, I'm going to write x1, x2, and then you can plot the level sets of the densities. The level sets could be like this. People know about the level sets of function. So this is, for example, where the density is like maybe like 3. This is where the density is like 1.5. This is where the density is 0.5. This is where the density is like 0.1. Okay, so the location of the points on which the density is constant. So these are like the set of all x1, x2, such that f of x1, x2 is equal to a constant. That constant, you usually write it on these levels. In any case, so if I do that, then the variance, so if I have level sets like that, when I draw from this distribution many points, I would see like things here a lot and like scattered around here and so on. Okay, so if I have like level sets that look like this for the density, like very much like this, so a lot of the mass, so this is saying that the majority of the mass sort of is concentrated near 0 and on like around this point. So if you do sample, you get a lot of points here, outside less, but very few here. The level sets are very tightly like connected here. So that's usually you also like represent these by just scatter plots of the points. Okay. So the covariance measures like a property of this joint distribution. Again, it measures how close it is to collapsing into a line, basically. Okay, so something that's like this. So very like symmetric versus something that the level sets are like this. So the covariance of this joint distribution is much higher. Okay, in the extreme case, the level sets are like going to be like exactly like this, and in the extreme case, just maybe like a line. And so to tell you that when you sample from this distribution, how likely is it that you find the two coordinates linearly varying? Okay, so it's a measure of how linearly dependent they are. It connects with the linear dependence in a sense from linear algebra. So does that make sense? Right. So if it's like that, then there's not much information. If I observe x1 here, I can observe x2 anywhere else. But here, if I observe, for example, x1 here, it's more likely to observe x2 here. And so you could say more, you have more information about where x2 is. This is the case where basically x1 and x2 are sort of independent. So how do we measure this so it's like covariance is a property of just joint covariance. Is a property of the joint distribution of x1, x2 measures how close to a linear dependence the two coordinates are. So if they're stochastic, but if the covariance is high, then it's like the correlation is high, let's say. The covariance could be high because the variances are high, or the correlation is a better measure. But so we'll talk about that. So how do we? So I usually write something like that. How do we define the covariance? Remember, yes.
The expectation of x minus its mean, x1 minus its mean, and then multiplied by y mean.
Yeah, okay. So this is exactly like that. If I think of the centered versions, I center the first one, is going to be x1 tilde, and I center the second one, it's going to be centered version. So it's just the expectation of the product of the centered versions. Okay. So what I really meant about the strength of linear dependence, that's the correlation coefficient. So the correlation coefficient is defined to be this divided by the variance of x1, variance of x2. So this counts the variance. So this covariance could be large because they're really related. Or, so for example, if this is, whenever this is positive, this is also highly likely to be positive, then this is going to be large. If whenever this is positive, this is highly likely to be negative, this is going to be negative large. But if there's no relation between them, so if there's no relation, so if x1 and x2 are independent, this is independence, then the covariance of x1, x2 would be the expectation of x1 tilde times the expectation of x2 tilde. That would be 0 because these are 0 means. So in the case of independence, the covariance would be 0. When they're linearly dependent, it's going to be non-zero. This correlation coefficient is a better measure because this discounts the variances. So if I divide by the variance, by the root of the variances, this correlation coefficient is going to be always between -1 and 1. And the two extremes, 1 and -1, correspond to the case where this allows it to align or this underlying. The case of 0 is the uncorrelatedness. So it is not exactly independence, but if they're independent, it follows that they're uncorrelated. Okay, so that's sort of the covariance. It's a little bit tricky to understand covariance is. So covariance captures both the strength of linear dependence through this part of which is the correlation, and also it contains some sort of the variance information as well. So if the variance of x1 is large, it makes the covariance larger because this great sheer magnitude of it is going to be large. So you can think of the covariance as two pieces. The variances of the two and the correlation coefficient, which is the normalized version. This was fast, but hopefully you know about covariance correlation. Just a reminder. So what is the covariance matrix now? Yes.
Matrix of all the variances between different variables of the sense. Along with that, it's just a variance.
Right. Yeah. So okay, can you say the last part? Great. Okay. Yeah. So you could say, if I want to summarize all the information here about this, I have the covariance between the two, and I also have the variances. I can put them in a matrix that contains all the information I need. Okay. So if I look at this, like x1, x2, the covariance matrix of this is one that has the covariance of x1, x2 here. The covariance of x1, x1 here, which is just the variance. So the variance of x1, the variance of x2, and the covariance is symmetric, so it will be x2, x1, but this is really the same as the other. Okay, so for a single, like two-dimensional, but for a two-dimensional random vector, the covariance matrix is the diagonal, and the variances, the off diagonals are this covariance between the pairs. You can in general define it to be the covariance, so this extends to n random variables. The covariance would be an n by n matrix. So if I call this x bar, this is like the matrix. So sorry, vector. So the ijth element is defined to be the covariance of xi, xj. Okay, so it's a matrix whose ij element is the covariance of the I coordinate of x and the j coordinate of x. And again, as was mentioned, what was your name, by the way? Joseph. Okay, so as Joseph mentioned, the diagonal elements would be like covariance of xi, and so this would be the variance. It's easy to verify. If I like do x1 and x1, this is going to be the same as the definition of the variance. So you get a matrix whose diagonals are the variances, and the off diagonals are covariance of like xi, xj. And this matrix is going to be symmetric because covariance of xi is equal to xi, xj is equal to xj, xi. You can see from the definition, if I switch x1 and x2, it doesn't change. So it's going to be a symmetric matrix. Is a symmetric matrix. Okay, so it has a lot of other properties that next time we're going to come back and talk about. Okay.